Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Project Design to Delivery in Difficult Geology Setting. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia recognises the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's long-standing industry partner, McConnell Dowell. For more than 60 years, customers have been coming to McConnell Dowell with complex projects that require innovative solutions. That's why they're known for their creative construction. From remote resources and energy projects to city-shaping infrastructure, they've built thousands of quality assets and facilities. Engineering-led, their expertise has grown steadily to span building, civil, electrical, fabrication, marine, mechanical, pipelines, rail, tunnel, and underground construction. With over 3,000 employees in the professional engineering and construction teams in Australia, New Zealand and Asia, McConnell Dowell benefit from a combined local knowledge and international experience. Today, we will hear from two speakers, followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker, Niall McNulty. Niall is a civil engineer and fellow of Engineers Australia with a background in the design and construction of major infrastructure projects in Australia, the UK and Ireland. Beginning his career as a designer for utility relocations for highway projects in the UK before gaining experience on tunnelling, light rail, motorway and major port redevelopments in Australia, delivering multidisciplinary design support during the construction phase. Niall has worked with McConnell Dowell for over 7 years, delivering permanent and temporary works for complex infrastructure across aviation, road, rail and port infrastructure sectors as an engineering manager. He was responsible for the development of the temporary works approach for the new Bridgewater Bridge project in Hobart, Tasmania. Please welcome Niall McNulty.
Thanks very much, Amanda. Thank you for the introduction and the opportunity to talk to everybody here today about what is a pretty amazing project. So today, the presentation from myself and my colleague Toby Cuthbert Ashmore, we split it into two. I'll go through a bit of the project background, our overarching methodology for the construction, how we assess the different bridge options based on the challenges we had at hand, and go through how we developed our construction access, basically the crux of the job. And Toby will take that on from there as to how that construction access was put into practice and installed on site, and how the piling construction went throughout the delivery phase. And I'd like to make an acknowledgement of the country. This is for the traditional custodians of the various lands of Meath today, Aboriginal and Torres Strait Islander people participating in the meeting. We pay respect to the traditional owners of this land, the Muinina people, and we pay respects to their elders past, present and emerging, celebrating their ongoing culture and enduring connections to country in the Bridgewater area in Tasmania. Australian and Tasmanian governments have committed 786 million to the new river crossing of Bridgewater, which forms a vital link on the main road between Tasmania and Launceston across the island of Tasmania. And it's essentially going to be one of the largest infrastructure projects that has been put together in Tasmania's history. So some of the benefits and what the new bridge will build or bring, it's essentially filling in a missing link where we've got motorway or dual carriageway standard roads on either side of the River Derwent, north of Hobart. and the bridge will create a 2 lanes in each direction and have interchanges both north and south of the river at Granton and Bridgewater. And the features are really to bring the speed up to 80 kilometres an hour from the current 60, a shared path for pedestrians and cyclists to create greater interconnectivity between Bridgewater and into Hobart. The navigation clearance will be consistent with the Bowen Bridge downstream, which will allow for unimpeded access upstream of the river, which is currently not the case. Further grade separated interchanges, the Brooker and Lyle highways, and really upgrading the connection to local highways, off to the west, and the local community in Bridgewater and Granton itself. So how do we build a bridge? Play a short video to really set out how we've gone about constructing the bridge from start to finish. The detail within the presentation will focus on the early part of that story with regards to setting up the marine access, how we've got out into the Derwent estuary, and then how we've delivered the piling works to build the foundations for the bridge. But the video will give a really good synopsis of what the bridge entails, what it is we're trying to do, and how we're going about it. So hopefully that video gave you a good overview of what it is the project is trying to achieve. So we'll get stuck into a bit more of the detail around what are the particular challenges that this location and this project have brought to us. So the new Bridgewater Bridge sets out to provide a smooth interconnection between north and south of the River Derwent and connect the communities there inwards into Hobart. And really, our goals for the project are to maximise that interconnection with local highways, minimise the impact on the existing causeway and the existing road users, minimising impact on the local community in general during construction. So maximising the speed limits as we go through there, keeping the traffic flowing. Within the Derwent estuary itself, we do have a lot of environmental sensitive receptors, including flora and fauna, a lot of black swans in the area. Seagrass is an important habitat for the local fish population. So where we had set out to construct with as minimal an impact as possible on both the people and the environment in the local area. So doing that, we optimize our bridge construction, and we're trying to rationalize what construction access we need for logistics and heavy lifts, etc. There's a view of the Derwent looking to the south. So the existing bridge is to the right-hand side. It's a piece of engineering heritage for the country. It was built in 1947. I believe it was one of the first welded bridges of its kind, and it essentially got a raising and lowering section in the middle to allow marine traffic through. So you can see in the foreground on the Derwent, it's got a navigation channel which is slightly deeper. The majority of the width is across the mud flats. So in the centre of the picture, you can see the change from the bridge structure through to what is a causeway, which was constructed by convicts in the early 19th century. So that causeway and corresponds with the area of mudflats where we didn't have much of a draft for construction access with barges and the like. So I'm going into a bit more detail. This slide actually gives you a bit more of a project setting as to where it is. We're just to the north of Hobart, on the main link in between Hobart and Launceston in the north of the island, and you can see on the schematic on screen that we've got interchanges to the south in Granton, a smooth curved bridge that more or less cuts the corner on where the existing causeway brings the road across the river currently. And then we go across to the northern side where we have the Bridgewater community, which is currently through pass rather than bypassed. Then we connect into the dual carriageway at the very northern end, which heads on up to Launceston. So you can get a sense of the scale of where the project is and how that link is between north and south. How we're trying to do that as smooth as possible, which drove the positioning of the bridge, drove the curvature, etc. So in terms of bridge option development, go through some of the thinking that we had from the early days in the tender period through to the ECI, and really the crux of the job being the bridge driving everything around it. We really set out to look at what sort of form of bridge did we want to construct in this area, understanding all of the geographical context that we were dealing with. So we did narrow it down to more or less three main options, with a super U, an eye girder, and a box girder. And the schematic there gives you a bit of a flavour of the differences between them. The super U and the eye girder primarily relied on having a headstock on top of the piers, whereas the box girder is more than likely going to be on top of monopiles that are independent of each other. So we had to look at what has been done recently in the market in Tasmania, and having a real Tasmanian focus. What sort of skills are in the market? What could we deliver in the local market? And where else within the country could we bring in skills from? Where were there Australian examples of these types of bridges that have been done well in similar types of estuarine environments or wide river crossings? and really our goal was to minimize our construction effort over water, and meet the construction window for traffic on the bridge, which was relatively tight. So as part of our optioneering, looking at some of the pros and cons of each, the schematics at the bottom start to introduce where we start to think about the temporary work. So shown is essentially how we might bring out the super U units, how we lift them into place, and where we do our piling from. So that would be off a temporary bridge, which is shown in grey, with a series of piers. So essentially, we're at an early stage where we're looking at what the bridge option is, how we construct it, tying the two together. Our teams were integrated to ensure that there was no one aspect was driving this. It had to be developed hand in hand, and you'll start to see where we come out the other end, how it's gone on this journey. With the Super U itself, we did have some local, well, certainly not local, but Australian examples where it had been done well. It is relatively simplified. The lifts were heavier though, and up around that 175 tons. So that meant that we'd probably have more piers, which meant more piles, and our piling risk was certainly increased. With the eye girders, we were able to get a larger span. So in that sense, we reduced the number of piers from 27 to 21. That meant less piles, but we did have potentially a lot of work to be done over water with the superstructure. So from a piling perspective, this was the direction we wanted to go in, but we did feel that the superstructure was probably going to be more complicated than we wanted to entertain. And box girder construction, which I suppose the photos at the top will give away that's where we actually went, but ultimately similar span to the U trough, but we did have less piers, or sorry, greater than the U trough. We had 21 piers, same amount of piles as the eye girder, but less overall than if we had gone with the U trough. And from our perspective, I think it was going to provide a more aesthetically pleasing structure that would fit in with the environment in a better way. So we were keen to push this along. It also was, it may have been more expensive in the cons, was something that we felt we had a better understanding of the risks around this. So the piles were potentially a bit larger, but we had less of them overall. This was going to be a monopile solution. It didn't require that we had to have multi-pile and complicated headstocks or complicated pile caps in the water. So we went with this solution, pushed the solution to the fore. So on screen gives you a little bit of a flavour for the geological setting, and on the right hand side is the pile design showing the reinforcement. So in general, we've got large, very deep riverine sediments with little or no strength, and we're trying to get down into the underlying rock. So we ultimately had a big piling challenge ahead of us. Piles were going to be long. The pile cages were going to be heavy and complex, requiring multiple lifts. So the ability to construct from something that was, let's say, a fixed platform that minimized the interaction with or the limitations imposed by tides was going to be a key factor in defining how are we going to go get out and actually construct these piles and piers. So at the end of our option analysis, we had essentially knocked out the U trough. You can see in the bottom left hand side, simple risk rating, which we've all seen, but ultimately we narrowed it from 3 down to 2. We did bring the eye girder solution through to a reasonable level of completion, but we ultimately went with the box girder, even though it may have been slightly more expensive up front, but in terms of a risk profile, as a project, we felt we were much more comfortable in understanding how we were going to go about the project. We felt we understood the risks much more. It was a known quantity in terms of a solution, whereas the eye girder was more than likely going to result in some much more work over water and exposure to personnel, and potentially result in more piles if we were to minimise the pile size, whereas the box girder allowed us to have a fairly relatively consistent pile size, translating up into the pier that you can see on the screen there. So in terms of marine access or riverine access, really, how did we go about the construction, and how do we intend to be able to deliver our piling, which Toby will go into in more detail in his presentation. And the approach for the project is really to work with nature rather than against it. So understanding that the big limitation really on this was the presence of the mudflats and the impact that tides would have. So we understood we weren't going to be able to take a traditional, barge construction approach where we've got floating plant, build a load-out platform, etc. On the northern side and the southern side, we didn't really have a lot of real estate to be able to build out load-out platforms or lay down. So what we came up with was a solution which utilized a temporary bridge on the northern side, which is that area number one. So where we're going across the river channel, where it's deeper, we've got a solid platform, again, that is not impacted by tides. It goes essentially the same length, about 365 meters, as the existing bridge across the navigation channel. And then that is interlinked with a series of barges, 12 barges, two sizes to fit in between the piers, which they themselves are interlinked then with a bridge in between to allow continuous access. Those barges will be interlinked, spudded, and grounded on the mud, so that we didn't have constant movement of barges coming in, churning up the sediment, damaging the seagrass. Once they were in, they were fixed. And then at the very southern end, where it was going to be quite difficult to get a barge in against the existing rail corridor, we have an area of reclamation that comprised of mass soil mixing, stabilization with an embankment on top of it with rock protection around the outside. So the temporary bridge, as I said, fixed all weather access, so no impact of tides, and it minimises the impact of weather because we're not working on a barge. We're potentially having to take account of the movement of the barges on cranes, for example. So it really gave us surety of logistics, and the fact that it could interlink between the north and the south. We have the option of going round on the local roads, obviously, but if we need to open up access from north to south, we can certainly do that. It gave us more flexibility in that sense. In terms of stability and challenging heavy equipment, for the piling equipment, we obviously we're utilizing a 400-ton crane because we're talking about significant pile casings, 2.5-meter diameter, 50 tons to get down through those soft sediments. The pile cages themselves at their heaviest, when you've got your final lift, you're lifting over 100 tons sitting within the pile. So we had significant lifts, and we wanted to maximize the construction safety aspects of this. A lot easier to work off a fixed platform, something that's nice and solid, and we've got space on it than it is if we're working off floating plant. And really, it maximized program reliability. We felt we had a tight program to get traffic on the bridge by the end of this year, start of next year. So we wanted to eliminate the impact of any unknowns such as river conditions, tides, etc. So as you can see, it's positioned to the across the navigation channel. So it spans across 36 spans of the temporary bridge altogether, based on about 13-meter spans themselves. We needed to understand how we could keep the river open, so we had to set it to a height where river traffic could actually pass underneath it. There isn't that much river traffic, but for the duration of construction, punts can still go through as required for local fishers and keeping that open. We positioned it within the piers, as you can see, more or less along the central line of the roadway, because that meant we could maximize the capacity of our cranes for our piling, for our pier construction, etc. If we were out to one side, like some of the early examples or options that we had looked at, you needed bigger cranes, harder to source it in the local market, and then you probably needed to increase the size of the temporary bridge again, because you're chasing capacity for a much higher load. The constructability of the temporary bridge itself was absolutely key. So in terms of program, we needed this to be something that we could install as quick as possible, and we worked with our subcontractors quite closely in Tasmania to work through the fabrication challenges and the installation challenges to make sure we could get that in there to meet the program. The temporary bridge allowed us additional storage on the headstocks. We did have refuges. We looked at some other projects, one recent one in New Zealand where we had used a temporary bridge, looked at the lessons from there, where maximizing your storage and maximizing the ability of a crane to move itself out of the way, or equipment to be moved out of the way to let through traffic through, was absolutely critical. So we took those on board and came up with a solution where we optimized our offline storage and our offline crane positioning, and really the time on site, to actually get this installed. None of this is welded. It's all bolted together. Minimize connections over water, utilizing locating pins, and then using the actual concrete deck on top of it to lock the structure together from braking forces and the like. Just some shots of the temporary bridge being constructed as we piled out from the northern side with 1050 piles. And the piling was undertaken really before we had fully finished the site investigation. So we were establishing what sort of geotechnical risk we actually had in that northern side, which did help feed back to the design of the permanent structure as well. Some shots there showing the headstocks being lifted into place, and they're slotted over the top of the piles, and the cans essentially are filled with gravel to lock them into place. Get a sense of the scale with the people there in the work punts position. It's not a small structure. Essentially, Tasmania's biggest bridge that's been built in probably 40 years. So these are the crane beams. So that the bridge was optimized, obviously, to take account of how we were going to do our piling operations or our pier operations, where we would have most of the loads just from the cranes located over the top of the steel structure that would run down the side, transfer that into the piles. And then you can see on the photo on the right hand side, much heavier structure on the storage bay or the crane operating bay, where there was potential for spragging, for example. So as we were devising the temporary bridge design, we spent a lot of time across all of our operations in the superstructure, our piling, our pier construction, to bed down what was the best configuration of the bridge, what size it needed to be, how well cranes could operate on it, how were logistics going to operate on it, and run that through a series of workshops. Take on board the feedback, and then that was fed back into our temporary bridge design to optimize it. Some finished shots of the finished bridge, and piling happening in that middle photograph with the 400-ton crane sitting in one of the fingers, and a BG45 piling rig sitting off behind it. So to the south then of the temporary bridge, we had the barge causeway. Pretty interesting way of utilizing barges, certainly in the number of barges that we had. So we ultimately designed 12 bespoke barges of various of two sizes that were shown there, designed to just operate as a normal barge in an unrestricted by arena, and designed for floating and grounding operations. So in that sense, we looked at thickening up of the hull, the bottom hull, for example, in case there was the presence of tree debris or something like that that was sitting in the top of the river muds. So we basically wanted to have flexibility that we can float materials up the river as part of the construction delivery phase, and then we ballast them into place. If the barges ended up floating, we also had designed them that we could continue operation in a kind of standard barge operation regime, less than 2% inclination when you're floating, and the same applying to the grounded. That was taken into account with the sizing of our crane. Again, looking at what did the piling operation, for example, entail. Spoke about that 50-ton casing. So that was one lift where we needed to be quite close to the bow of the barge. That had impact on its stability. The pile cage, lifting of the pile cage as well. When we were grounded, that was I think 110 tons odd of a lift, probably the biggest lift we had on the project. And again, we're sitting quite close to the bow of the barge. What would be the stability impacts on that? So a large amount of engineering requiring geotech input, naval architecture input to define how best we can utilize the barges in the mud flats. So for the assessment of how it would work, again, previously flashed up that geotechnical section. So again, you're looking at extremely soft mud in for a significant depth. So really, we wanted to just utilize the mud like whether a stiffer water, for example, but not work against the mud. Just use it to our advantage. So could we essentially put water, ballast into the barges to sit ourselves down in the mud, minimize any displacement, but settle the barges in slowly, and then gradually squeeze water out of that mud and get to a point where the barges would still move, but they wouldn't react like we're in water. They would be much more stable. So even if we're, as I said, sitting at the bow of a barge or quite close to the bow of a barge and lifting over the side on an angle, the ability of the mud to react in that scenario when it's being compressed and squeezed underneath the barges, it reacts much slower than it would if you're lifting in water. So we were able to get higher capacity out of our crane. Meant we could push the scale of the piling operations, for example, with those cages and what we could lift with the cranes that we had. All interlinked and playing off each other in terms of capacity and what was in the permanent works and the temporary works. A brief shot here showing the beginning of the construction. On the right hand side, it shows how we intended and planned to bring the barges in and push them in against the reclamation. So they were brought in on the high tide, put it in place, and then we started filling them with water once they were in the right position, surveyed them relative to the piers, and we pretty much achieved a positioning of plus or minus 200 mil within the design, which was fantastic. The link bridge design then that sits in between them, so no point having the barges if you couldn't actually walk between them. This allowed us to not only was this for walking between, but ultimately this is what we did our piling off. So we needed to get as close as possible to the pile location. Use the BG45, which is kind of shown on the right hand side there. The bridges themselves, we designed them in house, fabricated them in Batam, and brought them over, and then we did further reassessments to understand what we could do to put heavier loads on them, like the BG45. It wasn't initially designed for that, but we essentially re-engineered, put some other controls like some crane mats on top of these, and that meant we were able to use them. But this allowed then, as the operations progressed out into the further and further out into the river, you still had a full access width for deliveries for concrete trucks, spoil trucks from piling, pile cage deliveries, etc., to access the piling front. And once it's in operation, and Toby will go into that in a bit more, but certainly when seeing it in action, a bit of a logistical triumph to be able to bring so much material and remove material from the piling, in and out off the barge causeway. Required complex control. You can see on the right hand side staging of concrete trucks in a very tight space. It it looks like a big area of real estate, but once you see a crane on it, there's not a lot of space actually left for operating. And at the very southern end, essentially a project in and of itself, but where we couldn't fit in an additional barge, we always needed some area of strengthening to protect the existing seawall on that southern side, which is essentially a crumbling dry stone wall along the existing rail corridor. So again, working with nature rather than against it, we sought to stabilize the in situ muds by using mass soil mixing, applying a binder, and putting sediment controller around the outside. So progressively working our way out from the shore. And under the particularly well, to cap that off, we then had a significant depth of interlocking geotextile layers and embankment fill material to give ourselves a stable platform under some of the areas of higher concentrated load. The middle photograph shows the plinth where we'd land our link bridge to transition from the reclamation onto the most southerly barge. So again, high point loads in there, a much stiffer foundation to put in on those plinths, precast plinths sitting on top of those timber piles. And in the area of highest crane use in the center of the reclamation, we also use some timber piles to just push down through the MSM and make connection with the gravel layers underneath. Well, thank you very much, and happy to field any questions that anybody may have.
Thank you, Niall, for a great presentation. I'd now like to welcome our second speaker, Toby Cuthbert-Ashmore. Toby is a project manager and structural engineer with experience in large infrastructure and engineering projects in Australia and internationally. He started his career as a structural designer after graduating from Canterbury University in New Zealand before making the move into marine infrastructure construction. Toby completed a 3-year stint on the Tideway Super Sewer project in London before returning to join the McConnell team, managing the marine and piling works on the new Bridgewater Bridge project. Please welcome Toby Cuthbert-Ashmore.
Thanks, Amanda, and good afternoon, everyone. My name is Toby Cuthbert-Ashmore, and I'm the Marine Area Manager for McConnell Dowell on the Bridgewater project. My team was responsible for all the piling works, as well as all the other marine-related activities, such as the installation of the construction access. First of all, thanks to Niall for doing a great job covering the side of the marine and piling works. Obviously a key element in getting my team up and going successfully. I've got just under 25 minutes to talk and we'll be covering the construction, engineering, methodologies, and most importantly, the people involved in delivering the piling works. It's a big scope with a lot of intricate elements, so I'm going to try and not get bogged down in the details. I'll be giving a general look and feel of the incredible piling achievements that the McConnell Dowell team and partners have accomplished over the last 18 months. So, starting with the early days. I joined McConnell Dowell back at the start of last year, moving to Hobart for the job. Tasmania and the project really caught the imagination of me and my wife, and being a Kiwi, I'm a big fan of small islands achieving major things. When you first get your feet on the ground, it always takes some time to figure out who's who in the zoo, what strengths and weaknesses you have in the team, and who or what is going to make life easier as you progress forward. The remote and wild nature of Tasmania is what makes it such a beautiful and stunning place. However, that obviously also has its own set of challenges. I remember talking to our crane supplier early on who said, "Mate, why would I want to send one of our biggest cranes to a tiny island halfway to Antarctica?" Fortunately, though, we managed to bring him along on the journey. We're very lucky in this project to have a project director in Peter Fraser, who's got inspiring construction and engineering knowledge from his adventures around the world, and a construction manager in Ed McPhillips, who's had a strong career in building some of the most impressive bridges on the east coast of Australia. The McConnell-Dowell team is extremely robust in marine and infrastructure engineering and construction, and that wisdom and knowledge is shared around the business through Niall and the in-house design and engineering team. We had an incredible superintendent in Sean Casey, one of those salty old powerhouses who's been with McConnell-Dowell for 30 years and is unflappable with his experience and cool head. A lot of the procurement had been done already by early 2023, and I was fortunate to have an intelligent and committed senior project engineer from Tasmania called James Cocker, who had progressed signing up a piling subcontractor, procuring materials, and getting robust concepts in place for how we were going to do the works. The piling subcontractor who was chosen was Cape Horn Piling, who had the experience and large equipment capable of performing the task of some of the largest board piles in Australia. The methodology for completing the piles went through many concepts, with Bauer BG45 drill rigs chosen as a preferred solution. This was due to their drilling speed, efficiency of movement when tracking between the pile locations, and their versatility in drilling through the varied geotechnical conditions. I just want to quickly touch on some of the other marine works that our team was juggling at the time. Niall has already described the design and choice of access, being the temporary bridge and ballasted barge causeway. And in the first half of 2023, we were flat out with finalising procurement and getting all this installed. Barges were fabricated internationally in Indonesia before being loaded onto 2 separate shipments of a heavy lift ship and shipped directly into the Port of Hobart. McConnell-Dowell's international procurement abilities is one of our significant strengths, and this is bolstered by having a fabrication facility in Indonesia, where we made the majority of the temporary works for the piling and marine works. From the Port of Hobart, the barges were floated up the Derwent River and into position, ready for ballasting as part of our access causeway. The temporary bridge was installed up until Q3 2023. It was an interesting juggle, having to feed the temporary bridge installation with materials or getting piling started at its northern end. Hobart is a really vibrant and exciting city, which has a really nice size and scale to it. Part of what I've really enjoyed about the project is seeing how the whole city operates, from the port to the roading infrastructure, and even how we had to work around the shipping schedules of the cruise ships and Antarctic supply vessels that frequent the city. This photo nicely shows the scale of the barges and heavy lift ship, dominating the surrounding city skyline. It's fair to say that works of this nature were relatively new to the Tasports team, and while they may have raised an eyebrow at the interesting stacking arrangement of the barges on the heavy lift ship, they did an excellent job of working with us to get the barges and equipment offloaded at the port and safely up under the Tasman Bridge into the worksite on time. So just an overview of the piling scope of works. This is what we had to deal with. There were 46 monopiles over the length of the bridge. I think the term monopile really had a lot of resonance with everyone involved, and everyone was very aware that we would only get one shot at getting these right. The piles had a steel casing of 2.5 metre diameter and 25 mm wall. The end 1 metre was a pile shoe of 40 mm thick steel. The pile casing extended down to the top of the rock layer, sometimes 45 metres below the ground, with a bored rock socket continuing below the toe of the casing. The rock sockets that needed to be bored below the casing were 2.38 metres in diameter, with the deepest sockets up to a depth of 45 metres from the toe of casing. The deepest pile was in the middle of the river at a total depth of 90 metres. 11,000 cube of spoil would need to be drilled out and disposed of, including 4,500 tonne of contaminated soil. 3,000 tonnes of reinforcing cages were required to be manufactured and installed, with 11,000 cube of concrete needing to be poured to finish it off. The ground investigation for Bridgewater was very thorough and included a 6-month campaign, with 4 borehole rigs and 4 barges at its peak. Shipping containers were filled up with all the different borehole logs, with designers and McConnell-Dowell alike analysing the details. Every pile location received a detailed borehole log, of the geotechnical conditions, which was highly beneficial when performing the piling works, as we generally always knew what to expect. So this slide just quickly details a summary of the different conditions and types of piling that were experienced across the job site. All the piles had up to 30 metres of pass and contaminated marine muds overlaying the more competent material, and this was dug out with drill rigs and sent off site for treatment. On the north bank of the Derwent, the geological conditions were good, with piles between abutment B and Pier 20 going between 13 and 26 metres into good high-strength basalt. Piling would be conventional land piling, using the BG45 rig. The northern third of the piers maintained these good rock conditions in basalt with piers 21 to pier 13. Some rock conditions even potentially getting up to 200 MPa, with only a couple of 100 millimetres drilled every hour. Piling would be done in the marine environment, with the BG45 operating off the temporary bridge. The southern river piles between Pier 14 to Pier 2, about 2/3 of the river, was the really concerning material. Cobbles and gravel layers above low-strength breccia, clay, siltstone and sandstone. Geological conditions were highly variable, with differences of up to 25 metres between pile lengths, even at the same pier, which are only about 13 metres apart. This was reflective of the river valley and the tumultuous manner in which material had been deposited over the millennia. Piling for the south side of the river was once again in the marine environment, even though half the time the mudflats were completely dry at low tide, with the BG45 rig operating off the barges. The land piles on the south bank of the river were a similar makeup of clay, siltstone and sandstone. The plan with the works was to split the piles into a northern and southern work front, with the BG45 rig and piling crew on each side of the river, working towards each other. Just to really emphasise the challenges of drilling and the variable nature of the ground conditions, particularly on the southern 2/3 of the river, this is the borehole for the deepest pile at Piad Al. You can see from the borehole in the space of 10 metres, the ground conditions go from weak sandstone to breccia, with some core loss thrown in, then to sandy clay, then more core loss, then more sandy clay, and then back to weak siltstone. The photo on the right shows the borehole at the toe of the P8L pile and the challenging looking material that was going to be at the toe of our 90-metre biggest pile. It's fair to say that we all had a few sleepless nights thinking about the upcoming challenges. One of the most interesting pressure elements of the piling works was the test piles that had to be completed to validate the designer Tonkin Taylor's assumptions. In the next few slides, I'll cover the test piling process and an unexpected addition that popped up. 3 test piles were required, split in the 3 main different geological zones of the project. A test pile was required on land in the good basalt conditions of the northern bank of the river. One was required on land on the southern side of the river in the marginal conditions of siltstones and sandstones. And the final one was required in the middle of the river at Pier 8, in the clays and breccias. The test piles were 1.5 metres in diameter, installed in the same methodology as the permanent piles. They were tested to failure utilising hydraulic jacks cast into the piles, also known as Ostenburg cells or O cells. The procurement of the O-cell jacks, as well as the testing methodology and know-how, was procured through Fugro. 5 540mm diameter O-cell jacks with a capacity of 2,000 tonne each were installed at the point of equal capacity in the pile, with a thick steel plate sandwiching the top and bottom of the jacks to evenly distribute the loads and push the top section of the pile up and the bottom of the section of the pile down. Fugro supplied a crack team of specialists who flew in from Singapore and the Philippines. They first installed the jacks to the pile cage and then attended site when the cage was being installed to connect up the hydraulic lines. After the pile had gained sufficient strength, they came back to site and performed the pile testing and record keeping, pressurizing the jacks and pushing the pile to failure over a period of almost 24 hours. As you may be able to tell from the photos, the area around the O-cell was highly congested with reinforcing steel plates and the 5 jacks. There was particular concern about concrete flowing through this zone and being able to avoid voids under and above the O-cell location. Fortunately, with the help of good quality concrete from our supplier Hazel Brothers and a great job of placement by the team in Cape Horn Piling, this issue did not materialise. Unfortunately, what did materialise on the third and thought to be final test pile was an unexpected concrete loss through a zone of unusually weak conglomerate during the concrete pour. The pile ended up taking about 50% more concrete than originally calculated. Standing out on the barges at 6 p.m. on a Friday evening, with the concrete level in one of your precious test piles dropping, is a situation that none of us wanted to be in. A decision was made to complete another test pile prior to Christmas 2024. Procurement and program challenges abounded, with the team coming up against Thanksgiving holiday issues, getting jacks out of America, and then the challenges of trying to get the pile complete prior to Christmas. Thankfully, we managed to get across the line, pouring the last test pile on Friday the 22nd of December. Testing was successful, with all required loads achieved, and the design subsequently signed off in early 2024. So now I'll focus more on the construction and methodology of building the works, from getting the steel casings on site, getting them installed and drilled out, and finally concreted and completed. Once again, this will be a generally high-level pass, with an opportunity for anyone to ask questions on more detailed topics at the end. The steel pile casings for the job were manufactured in China, with the team from McConnell Dowell's Shanghai office doing a great job looking after international procurement. A ship was chartered to deliver the piles directly to the port of Hobart, where they were unloaded and stored until we were ready for them on site. Here's a nice photo of our gun engineering team displaying the size and scale of the 2.5 metre diameter casings. A local subcontractor, Gradco, had the unenviable job of moving these monsters safely from the port through the city of Hobart and up the highway to our job site. Moving piles of this length in one piece is relatively unprecedented, and the fact that Gradco team did it quietly, safely, and without incident speaks volumes. Just to really put it in perspective, here is our largest pile casing at 48 metres long, framed beautifully by the stunning mountain Kunyani in the background. Now, getting such large piles on site, manoeuvred where they needed to be, and then vertical and installed was one of the first logistical challenges to overcome. It was easy to be overwhelmed by the scale of the casings and the size of the problem. Fortunately, we had a very strong logistics manager named Mark Howell, and coupled with another very strong local senior project engineer named Sam Green, they came up with simple and effective solutions. Going back to the basics of lift planning and engineering, they spent time on site working with the supervisors and crane operators to safely single and dual pitch all the steel casings. The BG45 rigs utilised a piling gate or frame attachment to support the upper length of the casings and keep them safe and vertical until they could be satisfactorily driven to depth with a vibro hammer. Here's another one of my favourite project photos, a drone capturing an action shot of the two cranes performing a pile dual pitch with the Derwent River Valley and Kunani Mountain looking dramatic in the background. Bridgewater may not be in the Lonely Planet list of places to visit in Tasmania, but it really is beautiful and visually stunning. In the mornings and evenings, the sunrises and sunsets are spectacular. However, in the colder months, the weather can be absolutely unrelenting, with howling winds, thick fogs, rain and sleet, all funneling down the river valley towards you out in the open. None of this is particularly helpful for large crane work and high-risk lifting. For some of the more stubborn piles on the job, and particularly the longer steel casings, using drill and drive techniques with the BG45 rigs and vibro hammers wasn't enough to get them down to the required toe level. To achieve the result we needed, we mobilised McConnell Dowell's S280 impact hammer to drive the casings down to their final depth. The 2.5 metre diameter sleeve had to be specially mobilised and hired out of Holland. Here's a good drone shot of the hammer in action. While logistically getting this enormous 70-ton hammer set up and then moved around site was a major headache, I think the team liked the fun of using one of Australia's biggest impact hammers on some of Australia's biggest piles. As already mentioned, for drilling out the pile casings and then the rock sockets, the Southern work crew utilised a BG-45 piling rig, positioned on the temporary works link bridges that ran between the ballasted barges. Access platforms were welded on at different levels, one at barge deck level to aid in spoil capture and pile checks and inspection, and then an additional platform later, prior to the concrete pour, to provide access to the tremie. The rigs used rock and clay buckets on the end of telescoping calibars to drill out the casing and rock sockets. The material removed could differ greatly in nature, from the sulphur-smelling past muds to the clay-like remains of the drilled breccia and siltstone, and then finally the gravelly remnants of the higher-strength basalt on the north. The engineering and site surveillance of the piling work was robust at all times, with TNT supplying a geologist to monitor all pile arisings and confirm against the borehole log. An independent verifier had a separate engineer confirming TNT's checks, along with a strong engineering team of McConnell Dowell and our subcontractor, Cape One Piling. Similar plant and equipment were utilised for constructing the piles from the temporary bridge. The Northern work crew utilised a series of steel mats to strengthen the temporary bridge below and to support the drilling track pressures. The same sequence of temporary platforms supported on the steel casing was also used. Additional plastic segmental pontoons were implemented to stop any risk of spoil dropping into the Derwent, along with enviro controls of booms in the water. The depth and size of the piles meant that the piling rigs and other related equipment were working right at their limits. Calibars required constant inspection and repair throughout the work, as the high stresses and loads on them resulted in fatigue and damage. This was a particular concern at the end of the different stages of the bars. Agitator pumps used to clean out the base of piles were also an ongoing concern, struggling at the great depths. The depth, time taken to get to the base of the pile, and the size of the equipment was also problematic. While we had backups for backups on site, even just changing over a calibar or a broken down pump could take hours. The team were always focused on preventative maintenance and keeping the gear in as best as condition as possible. Maintaining the stability of the drilled socket was always paramount in everyone's minds. The fear of having an unsuccessful monopile that could then result in more piles and potentially a pile cap loomed large. Polymer drilling fluid was used in the weaker ground conditions of the southern piles from Pier 13 south. The polymer product supplier chosen was KB International, with the polymer having distinct improved environmental impacts over alternatives such as bentonite. The piling and engineering team leapt to the challenge of achieving the highest quality polymer possible, with our engineers and supervisors becoming amateur chemists, adept in the knowledge of pH and viscosities. The real beauty of the polymer product was its simplicity, with our McConnell Dowell project engineer, Prasanna Thavathis, doing an excellent job in using Tassie ingenuity to expand the farm up to a total of 1,200 cube by using locally supplied rainwater tanks. The mixing tank was an aerated shipping container from where poly pipelines ran the pumped polymer up to 900 metres out to the furthest extent of the polymer piling at Pier 13. Reinforcing cages for the project were manufactured locally in the north of the state by the subcontractor Bridge Pro Engineering. In total, 3,000 tonne of reinforcing cages were fabricated. Bridge Pro have many abilities, but making cages of this size and nature is unique and did come with a big learning curve. I think at one point in time, it seemed like they employed all the boilermakers in northern Tasmania to keep up with the fabrication and enormous amount of reinforcing welding required. 3D modelling, good drawings, and a simple production process was key in getting success, and by the end of the works, they were pumping out cages well ahead of schedule. To say the cages were absolute works of art is an understatement, and given their size and intricacy, they really did go together like Swiss watches. For the longer piles, the reinforcing cages had to be joined and spliced on site. with the standard reinforcing bar size being supplied in 18-metre lengths. Double rings of longitudinal reinforcing bars meant that site splicing and installation was very complex. The total final lengths of over 90 metres for the longer cages required the 6 cage sections to be delivered, pitched vertical, and then spliced and installed over the pile hole. The installation method was constantly improved to the point that all 6 cages and 90 tonne of reinforcing could be installed in a pile in a single day. Once the reinforcing installation was complete, the pile was checked and confirmed as still being clean and stable, and then the OK given. The concrete was placed via tremie pipe to the base of the pile, with the polymer fluid displaced and pumped back to the tank farm from the top of the pile. Concrete pours were large and often over 400 cube. Durations of the pour could extend up to 8 to 12 hours. We were very fortunate to have a dedicated batch plant from the supplier Hazel Brothers just up the road, and the plant manager Todd Rusher and team did an incredible job of getting the concrete supplied quickly and to perfect specification. Every single one of the loads was tested, and I genuinely struggled to remember a rejected load. Placement of concrete in the piles was so key to get correct, and with integrity testing being done on every pile, we had to make quality a major focus. Weekly meetings with Hazel Brothers and their technical team meant that the concrete mix and pour logistics were constantly tweaked and improved. The largest concrete pour was on our big 90-metre deep pile, P8L, with 426 cube of concrete placed in total. By this time, the team were finely tuned, pouring all the concrete within 8.5 hours at a rate of 50 cube per hour. The actual logistics of driving concrete trucks on the temporary bridge and barges was also a success due to the hard work and dedication of the McConnell Dowell site teams. Upon completion of the concrete pour, vacuum sucker trucks were used to remove the overpour concrete from the top of the pile. This method was a major win for the environment and health and safety, significantly decreasing the pile breakback that would normally be required for a pile of this size. I remember the old CEO of the company I used to work for in the UK visiting one of my sites and saying, "You know, one of these days we'll be smart enough to figure out how to avoid getting people on jackhammers and hammer drills." Now, I believe this method goes a long way to achieve what he was talking about. Through it all, we finally completed all the piling works in mid-July, with our last pile pour out in the middle of the river. It's fair to say that it was an emotional finish, with so many of the team having been here for the duration, and having put their all into getting across the finish line with a great result. I used to work with an old East London Cockney safety manager whose mantra was that all that really matters in this industry is the banter between mates and people looking after each other. While we all had occasional excitable moments out on site, I think this mantra of looking after each other and making sure that no one was hurt really rang true for the piling team, and we're very fortunate to have no major safety incidents as a result. Given all the challenges that we went through, collaboration and friendship was strong between different teams, McConnell Dowell and subcontractors, right until the end. So these are just the last few photos and last slide of my presentation. And once again, just a nice way to showcase and celebrate the people involved. Many of the McConnell Dowell team are still on the job, moving on to assist in other areas of the project, such as the superstructure erection and civil works. With works not complete on the overall Bridgewater Bridge until mid-2025, there's still a lot to do. But with a great team doing it, I have no doubt it will be a major success. Thanks for taking the time out of your afternoon, and I'll now hand back to the EA team so that we can get into the Q&A.
Thank you. Thank you to our great speakers from McConnell Dowell this afternoon. It's now your turn to get involved, so if you could please ask our speakers your question using the YouTube chat box and who your question is directed to. Thank you as always to everyone who submitted questions whilst registering. And I might start with a question for both of you, first for Niall and then for Toby. And it's a question that's come in from Daniel, and Daniel is watching from Victoria, asking you both, Could you please touch on some examples of the temporary works challenges, either shoring or propping, and how they were tackled to complement the permanent works? Thanks.
Thanks, Amanda. Yeah, I'll start off on this one. I suppose rewinding back to some of the options we looked at with the eye girder and the Super U, we were trying to move away from propping as much as we could. Some of those other schemes would have had essentially significant flying props to support the first sections of superstructure that would go up on top of the headstocks. Given the limited real estate we had with the barges, you could see how narrow they were, and the same with the temporary bridge, only the width of a crane. We wanted to avoid having to widen those logistical platforms as much as we could, because that meant more barges or more piles, more time to install all those things. So one of the benefits of going with that box girder solution was that we constructed in a balanced cantilever manner, that the only real propping per se of that system was in the first and the last spans. Both of those were on land essentially, and put up on false work. And then once we got up out of the ground with the piles, the temporary works that were designed to I suppose install the skirt, precast concrete skirt that covered the join between pier and piles. That was utilised then to sit the bespoke formwork that was placed on top of that. That increased in height depending on the pier, but it was essentially designed to be self-supporting by itself, sitting off that skirt. And then once we're up on top of the pier, you're essentially landing superstructure sections and stressing them down to the pier itself. So you're avoiding propping where you could, because you just didn't have enough room underneath because of the way we went about the construction.
Thanks, Niall. Toby, do you want to comment on that?
Yeah, so for the construction, I think obviously just the size of everything meant that temporary works challenges, they could be massive and significant, and often they could result in some really large and difficult to implement solutions. In these days and age, you have the 3D models where you can very quickly, easily design something up and it looks great, but before you know it, you've got this huge structure to lift down, fix down on site, move around. So it's really about just looking at what gear we had on site, what equipment, what machinery. I think we did a really good job of utilizing cranes and the rigs to really cut down on some of those kind of significant temporary works solutions. For those a bit more keen-eyed, you might have noticed in the little 3D animation, it had one of the old piling frames, a big steel structure that was originally designed to restrain and guide the pile casings during installation. For example, with that, we turned around and used the frame attached to the BG45 rig, which was a much simpler and quicker solution, much quicker and easier to move around site. Didn't have to kind of lift up, some kind of 50-ton structure, weld it down, spend days cutting it off, and then moving it along. Same with pitching the casings. There's sort of discussions around big pile pitching buckets and how we're going to do that, and that kind of got everyone a bit confused for a while. But once again, we looked at what we had, and we had big crawler cranes, and we had the ability to lift quite big objects and safely pitch them. So it's just sort of trying to minimise, not get too carried away with the solutions.
Thank you. And just staying with you, Toby, for now, we've had a question that's come in from Dane, who's watching from Queensland, asking you, Toby, how did you navigate local supply chain constraints in the delivery of the project? Thank you, Dane.
Yeah, I think, so thanks, Dane. It's a really good question. Just having to be organised and thinking ahead is probably one of the key aspects of that. I'm sure other people worked in regional areas around Australia, or even when I was working in London, had a poor procurement team. Sometimes it takes a week to get anything, and that's certainly true of Tasmania. It's easily at least a week from when you actually order something interstate to actually having it sitting in front of you. Generally, anyone who tells you any different is not telling you the truth. But it's all about just who relationships. We partner with good local transport companies. we had a really good person managing logistics, who I mentioned. Creating relationships with local suppliers and subcontractors all played a big part in this. That was certainly a real focus for the first sort of 6 months that we were getting set up and getting going. Tasmania has a very strong fabrication industry. So structural steel, temporary works items could be made locally. The precast planks for the temporary bridge were made locally. Pile cages we touched upon already. So whatever we could make locally, we did, and that was generally really successful and helped build those partnerships. Once again, we had good local subcontractors, Bridgepro Engineering, and then sort of out of state, we had the experienced piling experts of Cape Horn, and then sort of stepping up again, we had our international procurement ability, designing and fabricating large scale temporary works, barges, and it's a good solution to kind of overcome the supply chain issues.
Thank you for that. And a question for both of you, starting with you, Niall, and then Toby, if you could also comment. It's coming from Sue, and Sue is watching from New South Wales, asking you, if you were to redo the project again, what alternatives will you seek instead of a 2.5 metre monopile? Thank you, Sue, for your question.
Thanks, Sue. I suppose looking back at some of the things we considered, we were very keen to keep away from having multiple piles and having large pile caps that would then sit in and around that mud level and sitting in and out of the water. So whilst there wasn't a great water depth across those mud flats, it's you're talking about an estuary that's a metre wide. So we had felt in a constructability point of view was 2.5 metre diameter piles going to be challenging, deep 90 meters as Toby was noting. Once you had one in place, you were up and out of the ground, and the interface between the pile and the pier was going to be much more simplified with a precast concrete skirt, which is in of itself a 40-ton lift with some pretty detailed temporary works by Bridgepro to install that as to how we made the connection, how we rested the skirt on top of the pile and secured it in place. So I think, I'm not sure, certainly from my perspective, I'm not sure we would have taken a different route on particular aspects like that. Overarching, or looking at the bridge overall, I think to me, one of the pleasing aspects of where the project is now is the job is still doing what we set out to do in early 2021. So our methodologies have refined, but there's been no drastic changes. So as we planned and worked together between our engineering teams, designers across the board, our construction teams, and setting out in the early days of tender through the ECI period, what we've set out to do, we are still essentially doing and doing effectively, and ultimately aiming to we'll meet the program as required by the client. So I think looking at it from that sense, there might be some bits and pieces along the way, but nothing that would affect the change to what we're actually constructing in a macro way, from my point of view.
Toby.
Yeah, obviously easy for Niall to say, not out in the cold on the Derwent River, getting blasted by freezing wind, gritting your teeth as you're doing your monopile. But no, I think he's completely right. Fortunately, the design was robust enough. We had significant safety factors, and then it really helped us deal with construction challenges. Right from the early days, there's lots of collaboration between designers, with proof engineers, verifying designers, obviously the client DSG, working through potential issues and what solutions and mitigations would look like if any of those issues arose out on site. As I mentioned, we all felt the pressure of the monopiles. Having these mitigations in place and on site was really key. So some of those, for example, smaller buckets for getting through deformed casings, spare cali bars if we had things break, and even the worst case scenario, what to do if we had an unstable shaft. So we sort of came up with this solution and idea, and one of them was backfilling with low strength concrete. And this did actually occur on one of our piles when we weren't able to get the shaft stable. So when we wanted to implement that solution, everyone had already thought about it. Sort of, you still got to go discuss things with the designer and the client, but everyone had kind of processed that idea and what it might look like, and it was a much quicker approval process to make sure that we're doing the right thing on site immediately, rather than getting stuck and just turning wheels trying to get people to make decisions. So yeah, that was a really, really key process, and very, grateful that everyone took the time up front to work through it. In reality, I think smaller piles still needed to go down into the challenging and less stable material. As I said, the sort of 20 or 30 meters of mud, and then you're into cobbles, and there's no piles that were going to be founded, and would never be able to go into that material. So still would have been into that kind of 50 to sort of 70 meter depth. And it just would have extended the amount of time, more piles, who are at risk from hole stability, weather, plant breakdown. I think we would have preferred the kind of high pressure, shorter time frame than just being out there for longer, struggling through it.
Thank you for that. And another question that's come in for you both, starting with Niall and then you, Toby, reflecting on the project again. A question from Stefan from Victoria, who's asking you what lessons has been learned from the use of multiple barges as a temporary working platform for the pile installation. Niall.
Yeah, good question, and I suppose it took a large portion of my engineering career thinking about how is this going to work? Would it work? How well it would work? And ultimately, I suppose that question was based on would they float? Would they sink? Would they tip over? Would you actually get enough room to be able to work off and allow Toby to deliver piling and the other engineers on site to deliver the subsequent works? I think a couple of key characteristics of how the barges were intended to.
Right, okay. Thank you. Just unfortunately, we're facing a technical issue. We had about 10 minutes to go, but we have lost connection with our speakers, Niall and Toby. Just hang fire for a couple of minutes and hopefully we can get them back. If not, we'll come back to you and explain a bit more. But thank you for your patience. No, I'll ask this question for now. Toby, hi, Toby. The wonders of technology. Sorry, I think we've lost Niall temporarily. We didn't have long to go, but I have got a couple of some great questions that came in for you. One that came in from Dave asking, is there a requirement for dynamic pile testing or the like? And if so, how did you tackle this in this environment? Thank you, Dave, for that question.
Yeah, so I kind of touched on the pile testing process during my presentation. It was a combination of test pile, where we had the 3 that became 4 test piles done to verify the design. So essentially that's dynamic live testing of the pile using the hydraulic O-cell jacks. But then there was sort of end of the dynamic testing. Once we'd constructed the pile and poured the piles, it moved to doing integrity testing. So using pit testing and CSL sonic tube testings. So those are the 2 methods we used. All piles had both methods applied to them. And yeah, it was a successful way of showing that piles are in good condition.
Thank you for that, Toby. I'll ask you one more question, and then maybe I'll ask you to do, key takeouts from. Oh, with Niall, you're back. Lovely to see you.
Apologies,
I
yeah.
might just. Yeah, that's okay. We have a question now that's coming for you from Terence, who's asking you, noted that both permanent and temporary bridges run above the channel, which involved a preparation works to deliver and install the bridges. I'm just wondering whether the designer considered the option of building a submerged tunnel instead of a bridge. Thanks, Terence, for your question.
Yeah, interesting question, Terence. I think the genesis of the project will kind of, I suppose it moved from having what was the bare minimum you could actually construct. So there were some schemes initially that would have utilized the existing causeway. So building a potentially a bridge alongside the causeway and rebuilding the old bridge and reusing the causeway. So trying to produce a cost effective project rather than I suppose what would be more expensive in terms of tunneling through a rift valley like that. But obviously the bridge where we've ended up, it has gone on a significant journey from utilizing that causeway because more so the risk that we saw around utilizing or relying on the existing causeway because it's essentially sitting on that mud. We we moved towards a bridge that would give us better interconnection from north to south, but then from a geotechnical point of view, aligning the superstructure or pier construction or temporary works with how we wanted to do the piling. That choice of piling, we still felt that a pile solution for a bridge was more aligned to what our client was really looking for.
Thank you for that. And we are coming to the end of this afternoon's webinar. So starting with you, Toby, and then Niall, if you could just leave our audience with the key takeouts of your presentation, because we've certainly covered a lot this afternoon. Thanks, Toby.
Yeah, just as I was sort of trying to summarize, it's the people you work with and the interesting characters you meet along the way in engineering and construction. And when you've got a good team, you can really achieve anything. Combine that with good planning, all the expertise that McConnell Dowell has. That's really how we got to win out there. So yeah, just really emphasizing those points.
Thank you. Thanks, Toby. And Niall, if you'd just like to give us your key takeouts and also any advice you may have for our young engineers coming through the ranks and looking at these types of projects for the first time. Niall.
I really echo what Toby had said. I mean, this project for me has been a significant chunk of my career, and the people on it that I've dealt with over the last number of years, it's been universally fantastic. As a technical challenge, it's been immense. We've come up with some really interesting solutions, and to be able to do that, it really requires people to work together. So, whether it's the strong relationships Toby and I would have together and how we work through problems right across the board, those relationships exist from top to bottom within the project team, within McConnell Dowell, and with our subcontractors and suppliers as well. And I think that's been consistent from the early days of the project. I mean, it was COVID was still raging when I joined the project, and as I said, the thinking that we did back then, and how we approached the tender with our client and worked with our client, it's still we're still achieving that, or we're still delivering that as we speak, which I think speaks volumes of how we've gone about our work. And in terms of young engineers, I mean, this is the kind of job that, well, certainly it gets you excited. I mean, you want to get stuck into something. There's so many facets to a project like this, whether it's temporary works, whether it's permanent works, whether you want to be out on site in the cold and wet with Toby, or you want to be safe in the office with me. There's a million ways of achieving what you want to achieve in engineering.
It certainly is, and thank you for that. And it is all the time we have for today. And I'm delighted to say that we had almost 1,300 people registered for this webinar. So it's great that it's generated this level of interest. Please join me once again in thanking Niall McNulty and Toby Cuthbert Ashmore for their time and input. I'd also like to thank Engineers Australia's industry partner, McConnell Dowell, for their ongoing support.